Welcome to the class. Dear students, today we are going to discuss on isomerism. In this class, we will see what is isomerism, what are the two types of isomerism, in these types, what are the subtypes of isomerism, and everything we are going to discuss with examples. So let us start isomerism. Isomerism are compounds that have got same molecular formula. The molecular formula is same, but they are different in either one or more of their physical and chemical properties. I repeat, isomerism, they are compounds that have got same molecular formula, but they may be different. They are different in either one or more of their physical and chemical properties. Okay, so that is the definition of isomers. Okay, so isomers are those, and the phenomena is referred to as isomerism. So isomerism can be because of two reasons that this phenomena can occur. First is, it may be the case that the connectivity of atoms in the molecule is different. When I say the connectivity of atoms, what I mean to say is that the arrangement of atoms within the molecule, that is the way the atoms are arranged within the molecule, that may be different. In that case, it may lead to isomerism, and such kind of isomerism specifically is called as the structural isomerism. Or another reason of isomerism is that maybe it is that the connectivity is same, that the way the atoms are arranged in the molecule or the way the atoms are connected to each other, it may be same, but the difference is that the spatial arrangement, the way these atoms or these atomic groups are oriented in space, that may be different. And if that is different, such kind of isomers are specifically referred to as the stereoisomer, and the phenomena is specifically referred to as the stereoisomerism. So these are the two kinds of isomerism. This is the definition of isomers, and these are the two kinds and causes of isomerism. Let us understand structural isomerism and stereoisomerism by specifically discussing about these topics. So first, let us discuss about structural isomerism. So what is structural isomerism? As I have said earlier, structural isomerism, what is it? As I have discussed earlier, they are those isomers who have different connectivity of atoms, which have different arrangement of atoms within the molecule. Okay, so connectivity of atoms is different. So that is the first point. Connectivity of atoms is different, or the way the atoms are arranged in molecules. Suppose this is one molecule, this is second molecule. The way the atoms are arranged in molecule may be different. Fine. So the way the atoms are combined to each other, that may be different. So such kind of isomers are called as structural isomers. Now there are four subtypes of structural isomers. The first is chain isomers. Chain isomerism. Chain isomerism. Here, let me first write down the examples of chain isomerism, and then we will explain it. So this is the first example. This is N-butane, and this is isobutane. Look at this. This is isobutane. What is different in both of these? The way the carbon atoms are connected to each other, that is the only difference. That is why I said earlier, before discussing chain isomerism, structural isomers are different in the way the atoms are connected to each other. Right? Chain isomerism is specifically about carbon atoms. The way the carbon atoms are connected to each other are different. So here the way it is arranged is in a straight chain, and here the way that it is arranged is in a branched form. Okay, so that makes them chain isomers. Chain isomers, right? Some books are having a definition like this for chain isomerism, that these are those isomerisms which have different structures for carbon chain. That is also correct. It is having a straight chain structure, and this is having a branched chain structure. So now we have shown it using alkane. We can extend it to any class of compounds. So let me extend it to alcohol. Okay, so let me bring examples of alcohol. Let me first So let us discuss about this one. N-butyl alcohol, see. This is N-butyl alcohol. I am extending this chain isomers to other class of compounds here in the second example. So this is an isobutyl alcohol. This is N-butyl alcohol. This is isobutyl alcohol. Their molecular formula is same. OH is attached to first carbon atom here. Here also OH is attached to first carbon atom. Okay, so OH is attached to first carbon atom, that is same here for both. What is the difference? The difference is that here the carbon chain is different. It is a branched chain here and it is a straight chain here. So that makes it a chain isomer of each other. Okay, so chain isomers are those isomers in which there is a difference in the structure of the carbon chain, or there is a difference in the way the carbon atoms are connected to each other. Right? Here the carbon atoms are connected to each other in a straight chain, while here the carbon atoms are connected to each other in a branched chain. So that makes these as chain isomers. These as chain isomers. So that is the first subtype. Now let us go to the second subtype of structural isomer, which is positional isomers. Positional isomers. Positional isomers. Let me first write down the example and then we will see what it is. So this is the first example. This is N-propyl alcohol and this is isopropyl alcohol, right? This is 1-propanol and this is 2-propanol. N-propyl alcohol, isopropyl alcohol. Now what is the difference here? The difference is the position of the functional group is different. Okay, so positional isomers are those isomers in which the position at which the substituent atom or the substituent group is attached to the carbon chain is different. Okay, the positional isomers are those isomers which differ in the position of the functional group, which differ in the position of the substituent group that is attached to the carbon chain. An example of this is N-propyl alcohol and isopropyl alcohol. You can also extend the definition of positional isomers into alkenes. Let us see. So this is your butene, 1-butene, and look at this. This is 2-butene. Where is the functional group? Which is the functional group here? The double bond is considered as the functional group. Here the double bond is present between carbon atom 1 and 2, which makes it 1-butene, and here the double bond is present between the carbon atom 2 and 3, which makes it 2-butene. So here the position of the functional group that is attached to carbon chain is different. That makes 1-butene and 2-butene positional isomers of each other. Positional isomers can also be extended to di-substituted benzene having two functional groups. Let me first write the example. Look at this. This is the orthosilene, metasilene, parasilene. This is xylene, silene, orthosilene, metasilene, parasilene. So the definition of positional isomers can be extended to di-substituted benzene having two functional groups in which these isomers differ. These isomers differ with respect to the relative positions at which the two substituents are attached to the phenyl ring. These isomers differ with respect to the relative position of the two functional groups that is attached to the phenyl ring or the benzene ring. right? So this is positional isomers. So let us have a short recap of what is positional isomer. Positional isomers are those isomers in which the isomers differ in the position of the functional group that is attached to the carbon chain. So here we are seeing an example. This is N-propyl alcohol and this is isopropyl alcohol. Here OH group is attached to the first carbon atom, here OH group is attached to second carbon atom. So that makes it a positional isomer, because the positional isomers, the only difference is that it differs in the position of the substituent group that is attached to carbon chain. Now here look at this, 1-ene and but-2-ene. Here we have seen disubstituted benzene example. Here the isomers differ in the relative positions of the two functional groups that is attached to the benzene ring. So all these are examples of positional isomers. Now let us go to the third subtype of your structural isomer. The third subtype of structural isomer, which is, this is also structural isomer, functional isomer. Functional isomers. So functional isomers are isomers that are having different functional groups. They are isomers that are having different functional groups altogether. Okay, they have different functional groups. Their molecular formula is same, but they are having different functional groups. That is called as functional isomer. Or they are isomers that belong to different class of compounds. You can also say like that. They belong to different class of compounds. Let us see an example and understand it better. This is dimethyl ether, and this is ethanol. Both of its molecular formula is same. What is different is the functional group. Here it is an ether, here it is an alcohol. Let us look at the second example. This is ketone, acetone and acetaldehyde. Both of its molecular formula is same. The difference is the functional group. So functional isomers are those isomers in which the functional group is different, or they are those isomers which belong to different class of compounds. Here we have seen two examples: diethyl ether, ethanol, acetone, acetaldehyde. Pardon. So now let us go to the fourth subtype. The fourth subtype of structural isomer, which is tautomers. So tautomers, first let me write the example, then we will understand it better. So this is a tautomer, a pair of tautomers. Yes, this is a tautomer. Now tautomers are special type of functional isomers. Aren't they functional isomers of each other? Yes, because they are having different functional groups, right? One is a ketone, the other one is a enol, right? Not an alcohol. Okay, this is an enol. Enol is a functional group where OH is directly attached to vinylic carbon atom. This is a vinylic carbon atom. Why do we call it as a vinylic carbon atom? Because a vinylic carbon atom is that carbon atom which is directly attached to double bond. So that is why we call this carbon as a vinylic carbon atom. And enol is OH that is attached to vinylic carbon atom. So it is actually an enol group, not an alcohol. It is related to alcohol. So this is keto-enol tautomerism specifically. Okay, tautomerism are of lot of types. Keto-enol tautomerism, amide-imide tautomerism, amine-imine tautomerism, and lactam-lactamide tautomerism. All these types of tautomerisms are there. If you want to know more about tautomerism, please refer to my earlier video where I have discussed tautomerism in detail. So here we are going to see only on keto-enol tautomerism. So this is the keto group and this is the enol group. Both are actually functional isomers, right? So tautomerism is a special kind of functional isomerism, but the difference is that these functional isomers interconvert between each other. They interconvert between each other. and both of them coexist together at room temperature. Both of them coexist together at room temperature in a state of dynamic equilibrium. In a state of dynamic equilibrium. So that kind of isomers are called as tautomers, and that kind of phenomena is called as tautomerism. So this is the first example, acetone. There are other examples. Look at this example. This part is acetyl, this part is acetone. Okay, so this is acetyl acetone. Let us see how it undergoes. Pardon? Yes. So here also we have seen keto-enol tautomerism. This is the keto group and that is the enol group. Third example, let us see. Let us see the third example. This is the third example. This is ethyl aceto. This is acetate. Ethyl aceto acetate. This is the ethyl part. This is the aceto part. This is the acetate. Ethyl aceto acetate. So we have seen that acetone, acetyl acetone and ethyl aceto acetate, all of them shows keto-enol tautomerism. They interconvert into its functional isomer. Not only do they interconvert, they interconvert in a dynamic equilibrium. And this dynamic equilibrium only means that both of them coexist together at room temperature. You may be wondering why this arrow is longer and why this arrow is shorter. This is because this side, that is the keto, is more stable than the enol form. Therefore, the equilibrium will be always towards the keto side. That is, at a given time, more keto will be there and lesser enol product will be there, because the keto product is thermodynamically much more stable, and that is why the arrow is longer towards the keto side. Towards the keto side. To know more about this, please refer my earlier video where I have discussed. So where we were discussing about tautomerism, and tautomerism is a special kind of functional isomerism. Yes, these are functional isomers, but these functional isomers actually interconvert between each other and they coexist together at room temperature. So that is tautomers. Now let us go for the fifth subtype of structural isomer, which is metamers or metamerism. Metamers. The phenomena is called as metamerism. Metamers. Let us see what is that. Let us see the example and then we will go for a discussion. This is the first. What is the difference between two things? These are those isomers in which are different with respect to the carbon atoms on either side of the functional group. These are those isomers which are different. These are two isomers. They are different with respect to what? With respect to the carbon atoms on both sides of the functional group. Here the carbon atoms are 2 and 2 on the right and left of the functional group. But here the carbon atoms are 1 and 3, right, on the right and left side of the functional group. So these are those isomers which are different in the number of carbon atoms on either side of the functional groups. So this is actually propyl methyl ether and this is diethyl ether. So these are isomers of each other. Similarly, you can see, write one CO here, you'll get C. For ketones, this is propyl methyl ketone, this is diethyl ketone. So they are also metamers. So normally metamerism is shown by those functional groups which can be flanked by two alkyl chain like amine, ether. Okay, I hope you get it. Ketone. So these isomers, these functional groups can be flanked on either side by two alkyl chains. So such functional groups usually show metamerism. They show metamers isomerism. So that ends your structural isomerism. There are five subtypes of structural isomerism. The first is chain isomerism. The second is positional. The third is functional. The fourth is tautomerism. And the fifth is metamerism. We have seen all of them with examples. Let us now come to stereoisomerism, which is the second type. Stereoisomerism. Now, what is stereoisomerism? In stereoisomerism, the way the atoms are connected are the same. There is no difference. The way the atoms are connected, there is no difference in how they are connected to each other. They are connected in the same manner in both isomerism. The difference is how these atoms are oriented in space or how these groups are arranged in space. So that is the only difference. Otherwise, rest everything is the same. The way they are connected to each other, they are same. But how they are oriented in space, that is different. So for that, there are two subtypes. The first subtype is geometrical isomerism. Geometrical isomerism. So geometrical isomerism or geometrical isomers are those isomers which are different with respect to the way the atoms are oriented in space around the double bond. Around the double bond, not that double bond. So those who are having double bond, they will only show the geometrical isomerism. That is, alkene will show geometrical isomerism. Alkane or alkyne won't show geometrical isomerism. It is very clear from that definition itself. So let us first write down the example and then we will try to again understand the definition. So here I am taking the example of butene. So this is cis butene, and here we go for trans butene. This is trans butene, cis butene and trans butene. We can also take example of 1,2. This is dibromoethene. This is cis dibromoethene. And what about this? This is trans dibromoethene. Correct? This is something else. This is, what is it? Cis butene. This is trans butene. This is cis dibromoethene, and this is trans dibromoethene. Right? These are examples of geometrical isomers. What are they different in? Do they have the same molecular formula? Yes. Are the connectivity of atom same? Are they connected to same kind of atoms? Yes. Then what is different? The position of these atomic groups around the double bond is different. The position of atomic groups around the double bond is different between them. Here also the position, connectivity of atom is same. Molecular formula is same. Right? The way the atoms are connected are the same. The arrangement is same. But the way they are aligned in the space around the double bond, that is different. So that makes them geometrical isomers. That makes them geometrical isomers. There are a lot of other examples of geometrical isomers. You can remove this H and write chlorine. That would make it 1,2 cis 1,2 dichloro butene, and that's it. That's trans 1,2 dichloro butene, right? So this is cis 1,2 dichloro butene, and this is trans 1,2 dichloro butene. So you can make example like this. Another example of this is malic acid and This is malic acid, and this is fumaric acid. All these are examples of geometrical isomers. Malic acid and fumaric acid. This is malic, this is fumaric. So we can see that everything is same. What is different is the arrangement of atoms in the space around the double bonds. So such kind of isomers are called as geometrical isomers. So we have discussed geometrical isomers. Now let us go to second subtype. As I already told that geometrical isomers are shown by only alkenes, but it is not shown by all alkenes. It is shown by those alkenes which have two different groups on either carbon containing double bond. Let me write an example and we will try to understand. See, this is cis 1,2-dichlorobutene and this is trans 1,2-dichlorobutene. So it is shown by only those alkenes that are having two different atomic groups attached to carbon containing the double bond. Right? Two different atomic groups on either carbon should be present and a double bond should be present. Correct? So it is shown by alkenes like this, only alkenes like this, which is having two different atomic groups or two different atoms in either carbon containing the double bond. Suppose there is a difference in one carbon atom. Suppose this is the case, then this will not show geometrical isomers. Okay, it will not show geometrical isomerism. There should be two different atomic groups on either carbon containing the double bond. So alkenes of this kind would show geometrical isomerism. If there are similar groups on one of the carbon atom, it would not show geometrical isomerism. So that you should be very clear about. So now let us now go for discussing the second subtype of stereoisomer, which is optical isomers. Optical isomers. Optical isomers are isomers which are different in the way the groups are attached to each other in space, and they are so oriented in space that one is the mirror image of the other and that they are non-superimposable. Let me first write the example to make you understand this. This is lactic acid and its mirror image. Let me use a better marker. And this is this thing. Okay, so this is lactic acid and its mirror image. So optical isomers are those kind of isomers in which the isomers differ because the groups are arranged in such a manner. The atomic groups around the central carbon atom, they are arranged in such a manner that one isomer is actually the mirror image of the other isomer, and they are non-superimposable also. Okay, optical isomers result because the groups around the central carbon atom are arranged in space in such a manner that one is the mirror image of the other, and also they are non-superimposable. Okay, so you don't need to take a mirror image. Okay, no need to take a mirror image. They actually exist in nature like this. The difference between them is that this is arranged in such a way that it is a mirror image of this one, or you can say this is arranged in such a way around the central carbon atom that this becomes a mirror image of this one. And not only that, they are non-superimposable. They cannot be superimposed on each other. So if such is the case, then that kind of isomers are called as optical isomers, and that phenomena is called as optical isomerism. Now optical isomers are same in all the physical and chemical properties. They are same in all the physical and chemical properties. There is only one difference. Only one difference. And that difference in its physical property. One of its physical property is different. And can you guess the physical property in which it is different? Yes, it is different in its optical activity. It is different in its optical activity. What is optical activity? It is the activity that it exhibits on plane polarized light. It is the activity that it exhibits on plane polarized light. One of the isomers, maybe this one or this one of the isomer, assume it to be this, it exhibits an activity that rotates the plane of polarized light towards the right direction. In that case, that isomer is referred to as the plus isomer. And one of its isomer, assume it to be this, it exhibits an activity, it exhibits an optical activity that rotates the plane of polarized light towards the left direction, and therefore that isomer is referred to as the minus isomer or the levo isomer. So that is the only difference between the optical isomers. Rest all the physical and chemical properties are same. The only difference is one of its physical properties different. That physical property is the optical activity. And what is the optical activity? That means that one of its isomers exhibits an activity on plane polarized light. That is, when plane polarized light passes through one of the isomer, it may rotate the plane of polarized light towards the right. In that case, that isomer is referred to as the dextroisomer or the plus isomer. And the other isomer, when the plane polarized light enters it, it rotates the plane polarized light towards the left. That if it does so, that isomer is referred to as the levo isomer or the minus isomer. Now the words D and L or dextro and levo are not used. Plus and minus is generally used. Okay, the angle by which the plane of polarized light is rotated is called as the specific rotation. Specific rotation. It is denoted by alpha. Okay, at T degrees Celsius in D line of sodium light. So it is denoted by alpha. Now this alpha is constant for each compound. Okay, it is constant for each compound. It is different for different compounds, and it is constant for each compound and constant for each isomer of a compound. Okay, one may be plus and the other may be minus. So this specific rotation serves as the only parameter to distinguish between a plus isomer and minus isomer, because other parameters are same. So the specific rotation parameter, it serves as the only parameter to distinguish between a plus isomer and a minus isomer, because that is the only parameter that is different among these isomers. So that is the importance of specific rotation in determination of which isomer we are having at hand. Right? I hope you understand the importance. This is lactic acid and this is also lactic acid. Plus and minus, I don't know. The way to know whether it is plus isomer or whether it is minus isomer is only through experiment in a polarimeter. That means you have to make its solution and you have to pass the plane of polarized light through this solution to know whether it is a plus isomer or a minus isomer. You can determine or distinguish between the isomer. You can determine which isomer is at hand only through experiment. Okay, using a notebook and a pen won't work out. Okay, so you have to go for experiment in determining whether it is a plus isomer or a minus isomer. However, you can determine the configuration. Okay, configuration is different. Okay, so you can determine the configuration. So if I am saying the configuration of this, let me say, pardon for the interruption. As I was saying that for optical isomers, we were seeing the example of lactic acid. Now we can find out its configuration. Okay. For finding out its configuration, we need to see the atomic weight at the first point of difference. The higher atomic weight will get preference 1, will get the first priority. So here at the first point of difference, the atomic weight is higher for this, then for these both. When you look at the second point, this would get preference because it is having higher atomic weight, and 3 will come here, and this will be 4. So, and you have then to draw the arrow starting from 1, 2 to 3, right? So this will go like this. You can neglect the fourth one. So this is R configuration because it is moving in a clockwise direction, and here this thing will be it will be same, and here it will move in an anti-clockwise direction. So this is R lactic acid, and that one there is the S lactic acid. This we can say confidently, the configuration part we can say confidently, we can write it, we can derive it using a pen and a paper. But whether it is a plus isomer or a minus isomer, it can only be determined by doing experiment in a polarimeter. So if this is plus isomer, then this will be written as R plus lactic acid, and if this is minus isomer, then it will be written as S minus lactic acid. So if it is minus, it would be written as R minus lactic acid, and if it is a plus isomer, then it would be written as a S plus lactic acid. But to know whether it is a plus or minus isomer, we have to go for experiment in a polarimeter. Now the second example for optical isomer that I am going to put before you is glyceraldehyde. You might have seen the structural formula of glycerol or glycerine. This is glycerol. This one here is glycerol. So glyceraldehyde is nothing but you just take out this, and this is glyceraldehyde. That's it. So that's the difference between a glycerol and glyceraldehyde. Fine. So now the difference occurs here. This is the central carbon atom. Okay, this is one isomer, the other isomer, the groups may be arranged in such a way that the other isomer is a mirror image of this and is non-superimposable. So we get a structure like this. Now you can go for assigning configuration to it. So this will get number 1, you will get number 2, this will get number 3. So if you are drawing an arrow, this will be R because it is moving in a clockwise direction, and here the same scenario will be there, numbering will be same, and this will move in an anti-clockwise direction. So this will be S. So this is R glyceraldehyde and that is S glyceraldehyde. Both are optical isomers of each other. So but this is only the configuration of these. Whether it is a plus isomer or a minus isomer, as I said earlier, you can only know it if you do experiment in polarimeter. And this one also I would like to say the same. Suppose it is a minus isomer, then you can put it in brackets and that's it. You can indicate it like this, and if it is a plus isomer, then you can indicate it like this. But that you will only know after you perform the experiment. Now, as we have seen in lactic acid and in glyceraldehyde, both of these molecules are actually asymmetric. Asymmetric means that this molecule cannot be divided into two equal halves. Correct? So only asymmetric molecules, asymmetric compounds will show optical isomerism. Can I ask you the reason why these molecules are asymmetric? Have you noticed the presence of chiral carbon atom here? Yes, there is a chiral carbon atom. So chiral carbon atom is a carbon atom that is attached to 4 different groups, and that is why that compound is asymmetric. So for optical isomerism, the molecule or the compound should have at least one chiral carbon atom. Of course, there can be more than one chiral carbon atom. Tartaric acid have 2 chiral carbon atoms. So at least you should have one chiral carbon atom to show optical isomerism. Dear students, I hope you have enjoyed this session. I hope you have understood the class. If you have done so, please do not forget to like, share and subscribe this channel. Thank you very much.